In this video, we'll review the construction of a hierarchical model and discuss the questions that we can explore in the posterior analysis of this model. Consider an example. Let Y be the popularity of a song on Spotify, and suppose we want some sense of the typical popularity of a song on Spotify, as well as the degree to which popularity varies from song to song, and the degree to which popularity varies from artist to artist. To this end, we'll use a set of data that's grouped by artist. For example, our dataset contains multiple songs by Elisa, multiple songs by Frank Ocean, and so on. To reflect this group structure, let Yij denote the ith observed song for the jth artist in our sample. Then the first layer of our hierarchical model for song popularity addresses the smallest unit of observation, the collection of songs within each artist J. That is, this layer addresses the fact that we have 44 unique artists in our sample, and that we observe multiple songs for each of these artists. Specifically, the notation here expresses our assumption that within each artist J, popularity varies from song to song around some mean, μj, with standard deviation sigma y. Digging in deeper, notice the J subscript on the mean parameter mu. This reflects the fact that mean song popularity is artist-specific. Some artists tend to be more popular than others. Further, notice that the shared sigma y parameter lacks a J subscript. This reflects our assumption that, though some artists might be more popular than others, the variability in popularity from song to song is similar for each artist. That is, the artists are similarly consistent or inconsistent from song to song. Next, the second layer of our hierarchical model addresses the fact that our sample of 44 artists is drawn from the broader population of all artists on Spotify. Thus, these artists are linked through this population, hence information on one artist might tell us about another. Specifically, the notation here expresses our assumption that some artists tend to be more popular than others. That is, the typical popularity varies from artist to artist, or between artists, around some mean mu with standard deviation sigma mu. Thus, mu is the typical popularity of the typical artist, and sigma mu measures the degree to which some artists are more popular than others. The final layer of our model addresses our prior understanding of the global, or non-artist specific parameters, mu, sigma y, and sigma mu. Essentially then, these priors address our prior understanding of the general dynamics in the population of all Spotify artists, not just those in our sample. Bringing this all together, our hierarchical model addresses the variability in popularity from song to song within each artist, the variability in popularity from artist to artist or between artists, and our prior understanding of the dynamics in the population of all Spotify artists. Now, once we start our posterior analysis of this model, it's going to be beneficial to think about this model another way. Specifically, consider the second layer of our model, which describes how the typical popularity level, μj, varies from artist to artist. In this layer, μj represents the typical popularity for some artist J. Another way to think about this artist-specific mean is as a random tweak to the global mean mu. That is, artist J's popularity level is equal to the typical popularity level mu plus some tweak b sub j. The plot here represents this idea. Consider an example. Suppose that the typical artist has a popularity of 50, whereas artist J has a popularity level of 75. In this case, artist J's popularity level is 25 points higher than that of the typical artist. That is, μj is equal to the global mean of mu equals 50, plus a tweak of b sub j equals 25. Or, suppose another artist J has a popularity level of 40, 10 points below that of the typical artist. Thus, μj is equal to the global mean with a negative tweak of 10. Just like the artist-specific means themselves, the tweaks B sub j are random. Since the μj are balanced above and below the global mean mu, the group's specific tweaks are balanced above and below 0. Specifically, the tweaks are normally distributed around 0 with standard deviation sigma mu. With this in mind, we can express our model in two equivalent ways. In the first layer, we might note that within artist J, song popularity varies normally around mean μj, where μj is equal to mu plus b sub j. Then, we can swap out the model for the μj terms with the model of their corresponding tweaks, b sub j. From there, the prior models on our global parameters remain unchanged. Now that we've reviewed and expanded the construction of our hierarchical model, we're ready to do some posterior analysis. A natural place to start here is by exploring the global or non-artist-specific parameters. These are as follows. Mu reflects the typical popularity for the typical artist. Sigma mu measures the between-artist standard deviation, that is, the variability in typical popularity from artist to artist. And sigma y measures the within-artist standard deviation, that is, the variability in popularity from song to song within any given artist. In general, the analysis of mu is pretty straightforward. Yet the analysis and comparison of the variance terms, sigma mu and sigma y, is pretty unique to hierarchical models. Hence, the special name. Recall that the specific hierarchical model we've been studying here is often referred to as a one-way analysis of variance, or ANOVA model. It's so called because it allows us to analyze the different sources of variability in song popularity. Specifically, in non-hierarchical models, we can simply explore the total variability in popularity from song to song across all songs and all artists. However, our hierarchical model allows us to decompose this total variability into the variability from song to song within the artist and the variability between artists. In turn, this decomposition allows us to account for how much of the variability in song popularity can be attributed to differences between songs within artists or differences between the artists themselves. Specifically, dividing the within-group variance sigma y squared by the total variability in song popularity measures the proportion of the total variability in song popularity that's explained by fluctuations in popularity from song to song within artists. Dividing the between-group variance sigma mu squared by the total variability in song popularity gives us a measure of the proportion of the total variability in song popularity that's explained by differences in popularity from artist to artist, that is, between artists. Now, pictures really help us understand these concepts. Each plot here includes a density plot of song popularity for two different artists. These plots then represent three different scenarios for the decomposition of variance. Consider the first extreme in the left plot. In this case, the density plots for the two artists are barely overlapping. Thus, there are greater differences between these two artists than between the songs within either of the artists. Technically speaking, sigma mu is bigger than sigma y. Proportionally, then, most of the variability in song popularity in this scenario can be explained by differences between the artists, not between the songs within each artist. Consider the second extreme in the right plot. In this case, the two density plots for the two artists have very strong overlap. Thus, relative to the differences among the songs within each artist, there's little difference between the artists themselves. Technically speaking, sigma y is bigger than sigma mu. Proportionally, then, most of the variability in song popularity in this scenario is explained by differences among the songs within each artist, not between the artists themselves. In between these two extremes, the middle plot reflects a scenario in which the variability in song popularity is equally attributable to differences between artists and differences among songs within each artist. Finally, after understanding the global parameters, hence the patterns among all artists, not just those in our sample, we might wish to dig into the artist-specific patterns for those artists that are in our sample. To this end, we can explore μj, the typical popularity for each artist j. Equivalently, we can explore how each artist j compares to the typical artist. Specifically, we can explore b sub j, the difference between artist j's typical popularity and that of the typical artist. Now we've talked about the big ideas in this video. In class, you're going to dig into the details.